Okay, so let's come back to this problem. Let's finish it, and then I will have your questions if you have any more. Now, we have to solve this equation. We have to determine what those coefficients are. Now, of course, there is still the problem of on the left-hand side, we have a function of cosine theta. On the right-hand side, we have just a series of Legendre polynomials in cosine theta. Now, the question is it always possible to write a function of, let's say, cosine theta in terms of a sum over Legendre polynomials of cosine theta? That is the first thing we have to answer. Is it always possible? This is what we are called the completeness. So if Legendre polynomials are complete, then we can write any function of cosine theta in terms of the Legendre polynomials of cosine theta. Again, we are not going into the details, etc., but Legendre polynomials are complete. That is, you can always find, if you have any function, not necessarily a Dirac delta, any function of cosine theta, you can always write it as a linear superposition of PL of cosine theta. That is always possible. It's just like the Fourier theorem. You see, in Fourier theorem, what you do is if you have a function defined in an interval, you can always write that function in terms of sines or cosines. And then the next thing is you try to determine the coefficients. It's more or less the same idea, but instead of just sines and cosines, we are expanding this function of cosine theta in terms of PL of cosine theta. Now, once our friend has proven that it is always possible, the next question, what should be these coefficients? Now, what I will do is multiply both sides by sine theta PL prime of cosine theta and integrate over theta, integrate over from theta is equal to 0 to theta is equal to pi. That is what I will do. Well, why? Because I know this property of the Legendre polynomials. I know this property. So on the right-hand side, I already have the PL cosine theta. So I will multiply it with this function, integrate over theta from 0 to pi, such that the PL of cosine theta in that sum will be converted into a Kronecker delta, which basically tells me that there I have an infinite sum. Only one term will contribute after I evaluate this integral. So, if I do the same thing on the right-hand side, I would obtain 2 over 2 pi epsilon 0 d squared integral from 0 to pi d theta sine theta PL prime of cosine theta Dirac delta of cosine theta minus 1. This should be equal to sum over L I have this combination times 2 over 2L plus 1 Kronecker delta L L prime. Well, in the sum, I have this PL of cosine theta, but I'm multiplying it with PL prime of cosine theta and sine theta and integrating from 0 to pi. That just converts that PL of cosine theta to this factor over here. So I just wrote it straight away. Now that Kronecker delta basically tells me that in this sum only the term L is equal to L prime contributes, all the other terms are 0. So it is equal to 2 over 2 L prime plus 1 B L prime plus 1 divided by d L prime plus 1 plus a L prime times L prime d to the power L prime minus 1. Well, I still need to evaluate that integral over there in that line. Let me first make a change of variables. U is equal to cosine theta. On the first line. So if I make that change, the integral from 0 to pi of the theta sine theta PL prime of cosine theta, Dirac delta of cosine theta minus 1. This is equal to, well, if du is nothing but minus sine theta d theta. So here I have the sine theta d theta, that just becomes a minus du. When theta is equal to 0, u is equal to 1. And when theta is equal to pi, u is equal to minus 1. PL prime of u, Dirac delta u minus 1. Or let me just switch the order of limits. This is from minus 1 to 1 du PL prime of u, Kronecker delta u minus 1. Well, this is one of those, let's say, pathological cases where the Dirac delta is 0 on the boundary. But in this case, we have to assume that the Dirac delta is inside our interval. So this is equal to PL prime of u, PL prime of 1. Well, the Legendre polynomials are defined such that PL prime, the Legendre polynomials evaluate that 1 is always defined as 1. So that gives us this relation that, well, here what we had. The left-hand side of our equality is q over 2 pi epsilon 0 d squared. That integral we had just seen is 1. It should be equal to this expression over here. Now that's our second relation between AL and BL. Well, let me drop the prime over here. Whatever the value of L prime is, or L is, I have this relation. The other equation we had was this one. Or this tells me that AL should be equal to BL over d to the power 2L plus 1. I can put it there. Q over 4 pi epsilon 0 d squared times 2L plus 1. I just multiplied both sides by 2L plus 1 over 2. This should be equal to BL L plus 1 over d to the power L plus 1 plus BL times L divided by d to the power L plus 2. Well, I made a mistake where here, remember, this is 2. So this is not 1, this is 2. So all these are 2. Otherwise, the units wouldn't have matched. So that's why I saw that there was a mistake somewhere. Now we can just combine. This is equal to BL times 2L plus 1 divided by d to the power L plus 2. Now I can cancel these 2L plus 1s. This d squared cancels this one. So that gives me BL is equal to Q over 4 pi epsilon 0 d to the power L. And AL is equal to BL over d to the power 2L plus 1. That is Q over 4 pi epsilon 0, 1 over d to the power L plus 1. So we now know what BL is, what AL is. That is, we know our potential. So the potential inside was, if you remember, it is AL r to the power L PL of cosine theta. This is equal to Q over 4 pi epsilon 0, sum over L r to the power L divided by d to the power L plus 1 PL of cosine theta. And V out, this is BL over r to the power L plus 1 PL of cosine theta. We had determined what BL is, so this is Q over 4 pi epsilon 0, sum over L d to the power L divided by r to the power L plus 1 PL of cosine theta. This is our potential both inside and outside. Now I will do one aesthetic change, modification. We already know the answer to this problem. So it is, we had written it over here. This answer is correct both inside and outside the potential, this one. Let me define two things. I will call R large to be the maximum of R and D, and R small to be the minimum of R and D. So in general, R can be larger than D or smaller than D. Now, with this definition, V in is equal to Q over 4 pi epsilon 0, sum over L. Well, this is valid when we are inside the sphere, that is when R is smaller than D, but that is R small to the power L divided by R large to the power L plus 1, PL of cosine theta. And V out, this is equal to Q over 4 pi epsilon 0, sum over L. Now V out is valid out of the sphere. So when D is small, R is large. So this V out, we have D to the L. But when this expression is valid, D is smaller than R. So D is basically R small to the power L divided by R large to the power L plus 1. So basically, in terms of these new parameters that we defined, R small and R large, V in and V out have exactly the same form. Now let me do the same thing with this for this one. V of R is equal to q over 4 pi epsilon 0, 1 over r squared plus d squared minus 2rd cosine theta to the power minus 1 to the power 1 half plus 1 half. This is q over 4 pi epsilon 0, 1 over r large squared plus r small squared minus 2r small r large cosine theta to the power 1 half. Well, you see, one of these is r, the other one is d. So whichever one is r or d, we don't really care because this expression is quite symmetric in r and d. But now I will do a trick. This is q over 4 pi epsilon 0. I can take out the larger one, whichever one is larger. What remains inside is 1 plus x squared minus 2x cosine theta to the power minus 1 half, where x is equal to the small one divided by the large one. Now let's compare these two. This is one expression of the potential we have. The other one in this rectangle is another expression we have, and that we can also write in this form, q over 4 pi epsilon 0 r large. You see, r large has one more power in the denominator, so I just take it out. What remains is r small over r large to the power L. R small over r large is nothing but x. Sum over L, x to the power L, PL of cosine theta. Now comes the uniqueness theorem. Uniqueness theorem tells us that the potential is unique. No matter in which method you use to obtain which form it might take, they should be equal. Well, this basically tells me that 1 plus x squared minus 2x cosine theta to the power minus 1 half, this is equal to x to the L PL of cosine theta. Well, this is one expression that I had wrote in the lecture, just stating that it is defined to be so. Well, this is kind of the proof that it is so. Yes, any questions now? Well, let's start. This was the problem we had. We just wanted to solve this problem using separation of variables. Of course, along the way, we did define lots of things. And then we even obtained the proof that this square root is the generating function of the Legendre polynomials using the uniqueness theorem. This one? Well, if you know the properties or all the properties of the Legendre polynomials, yes, that's something we know. This is one definition of the Legendre polynomials. Another one is the Rodriguez formula.
Method of images'ı neden kullanıyoruz? Hangi durumlarda hani bu yöntemi kullanıyoruz?
You see, let me ask you this question. Suppose you are a repairman. Okay? So you have your toolbox. Would you like to go everywhere with a single tool, and if you cannot repair with that tool, you say that, okay, it's not repairable, or you would rather have many tools in your toolbox, and depending on which problem you have, you choose the suitable tool. That's what we are actually doing here. We are teaching you several tools. Method of, well, in your first year, we basically taught you just a single tool. Two of them. Take the integral of the charge density if you know them. That's great. If you can take the integral, etc., that works. And the charge density. And what if you have just conductors and point charges? You don't really know the charge density in the conductor, so you have to determine them. But if the conductors have some kind of a symmetry, if they act like a mirror, just imagine yourself that having a mirror in the shape of the conductor, and you are looking at the conductor from the position of the charge, would you see a well-formed image of yourself? Or just intermingled colors? If you see a well-defined image, then the method of images works. So you have one charge, you will have, depending on your configuration, you might have one image charge, several image charges. For example, we looked at the problem of an infinite plane or a sphere. Those gave you one image charge. In your homework, you are supposed to do the method of images for an infinite cylinder, and you have a single infinite wire in front of it. That also gives you one image charge. But if we also consider the example of two semi-infinite planes at 90 degrees, that doesn't give you a single image charge, but three of them, three images. So you can also solve that. Now comes another method, the separation of variables. Well, these are especially useful if you cannot apply the method of images. If you can apply the method of images, it's quite short. If you cannot apply the method of images, but still your boundary is simple to express, at least in a specially chosen coordinate system, then you can try the separation of variables. And we did examples on Cartesian coordinates and also in spherical coordinates. Well, we only didn't do any example on cylindrical coordinates. But it's also possible in cylindrical coordinates.
Hocam ben şey yapamadım. Bu equipotential surface'ı conductor'la değiştirip.
Well, that is the idea of method of images.
Hiç onu yapamadım.
Why not? Well, the idea of method of images is that given any system, that system will have certain equipotential surfaces. And if you replace that equipotential surface with a conductor, nothing will change in your system. But the conductor, a closed conductor, basically isolates the inside and the outside. So once you create your system, put an equipotential surface, and then you can remove the charges either inside or outside. In the other region, nothing changes. That's the idea.
Yani o conductor'ı koyduktan sonra point charge düşünüp onun image'ini alacak.
Which problem? In the homework, I think you had this two infinite wires, right? And let's say we have this infinite wire going out perpendicular to the screen with charge density plus lambda, this other infinite wire parallel to that one, again going to infinity. Now, one problem is where should we set the zero of the potential? Yeah, we cannot set infinity to zero because you see the potential difference between the point at a distance, let's say rho, and the point at infinity of a single wire is minus E dot dl. But the electric field of a these are single wires. The electric field of a single wire is just lambda over 2 pi epsilon 0, 1 over r dr from infinity to the distance r. But this is minus lambda over 2 pi epsilon 0 logarithm of r over infinity. Oops. It diverges. You cannot, at least for a single wire, you cannot set the potential at infinity to 0. For two wires, you can. We will see that for two-wire system, there's no problem at setting the potential at infinity to 0, but I would rather use the superposition principle and treat my system as the sum of two separate infinite wires. And for each one of them, I cannot really set the potential at infinity to 0. Now, let's look at my problem. Well, there is quite symmetrical, kind of. This point has a larger potential than this point, and the charges here are the negative of this one, so I would expect the potential to start from some value over here, and it will have the exactly negative of that value on this side. So in between, it will be a good choice to set the potential to be 0. So here is V is equal to 0 point. So let's say this is our distance d over 2, this is our distance d over 2. Now, if this is the case, you can just work out the potential. The potential at a distance rho from the wire, from both of these wires. Let's say at this point, this will be equal to lambda over 2 pi epsilon 0, logarithm of rho plus over rho minus. Let's say this distance here is rho plus, this distance here is rho minus. So that in the middle plane, at the middle point, rho plus is equal to rho minus, so this ratio is just 1, the logarithm of 1 is 0, so the potential there is also 0. When you go infinitely far away from the wires, not in the direction of the wire, but infinitely far away when rho goes to infinity, well, again, rho plus and rho minus, they will be equal to each other. So again, you will end up having the potential at infinity will be 0. Basically, because if you go to a distance infinitely far away from the wires, the separation between the wires will be negligible. It will just behave like a system of no charge density. Now, I'm kind of skipping the steps so that we can finish this problem on time. So do you have any questions up to this point? I mean, up to here, it should be kind of straightforward. How to calculate the potential of a given charge distribution, etc. Now, let's see. Let me put some coordinates. This is my point. These are my wires. So this is the point that I'm looking at. So this distance I called rho plus. This distance I defined as rho minus. I will choose the origin of my coordinate axis, midpoint between the wires. So this is my rho, and this is the angle phi. Now I will express rho plus, rho minus in terms of rho and phi. So the easiest way, let me define this vector as my rho vector. This vector, as let's say this is the x-axis, d over 2 in the x hat. This is minus d over 2 in the x hat. So rho minus is nothing but the magnitude of, let's say, the opposite of this vector. The opposite of this vector is this vector. If I add the rho vector to it, I get this vector from here to that point. So this is rho vector minus d over 2 x hat. This is rho minus, which is equal to rho hat minus d over 2 x hat squared to the power 1/2. This is equal to rho squared plus d squared over 4 minus d over 2 rho hat dot x hat, rho vector dot x hat, to the power 1/2, rho squared plus d squared over 4 minus d over 2. Well, the scalar product of two vectors is the product of their magnitudes. X hat has unit magnitude, rho vector has magnitude rho. The angle between them is theta. This is rho minus. Rho plus, well, rho plus is basically the same thing with d replaced by minus d. Now, for points on an equipotential surface, on an equipotential surface, the potential is constant. Look at the expression for the potential. This is a constant anyway. So on an equipotential surface, this ratio should be a constant. So rho plus over rho minus, this is a constant, let's just call it C. C can take different values, and depending on the value of C, your equipotential surface will correspond to different potentials, but for each equipotential surface, that ratio has a constant value. Or, let me take rho plus squared divided by rho minus squared, this is a constant. Well, the reason why I take the squares is that rho plus and rho minus, both of them are defined as the square root. I want to get rid of that square root. Rho plus squared is rho squared plus d squared over 4 plus d over 2 rho cosine theta. This should be equal to some constant times rho squared plus d squared over 4 minus d over 2 cosine theta. This is the relation between rho and theta. So let's just organize it a bit. Rho squared times 1 minus c plus d squared over 4, 1 minus c, plus d over 2 rho cosine theta, 1 plus c, this is equal to 0. Well, the easiest case is when c is equal to 1. When c is equal to 1, this is 0, this is 0. So this rho times cosine theta has to be 0. Well, rho is 0, it just corresponds to the line along the z-axis. Or cosine theta is equal to 0. Well, cosine theta is equal to 0, just corresponds to this plane. The angle is pi over 2. Pi over 2 or 3 pi over 2. So it's just this middle plane that is an equipotential surface. Well, for other values of the potential, it will be a bit difficult to identify. But let me just say that, let me just assume c is less than 1. If c is larger than, so that this constant is positive. Or let us even write it in this form. 0 is equal to rho squared plus d squared over 4. C is not 1, because we already solved for what happens when c is equal to 1, plus d over 2 rho cosine theta, 1 plus c. This is the equation we have. We need to kind of identify what are these points. Let me write it in this form. Rho plus d over 4 cosine theta times 1 plus c over 1 minus c squared minus d over 4 cosine theta 1 plus c over 1 minus c squared plus d squared over 4 equals 0. Now I'm trying to simplify it, but no, this is not the way. We can solve for rho, but I mean, rho in terms of theta, but it won't be easy to see what the solution is. What I would like to write this as rho minus rho 0 is equal to 8 times cosine theta. If I can write this in that form, well, in fact, I kind of actually did. Now, I will not continue, but this is the square. I mean, you can write this as the square of something. Oh, but no, I didn't do that. Now, the reason why I want to convert it to this form is this is the equation of a circle around rho 0. So this is the last thing done, last thing that needs to be done. So this is the equation that the equipotential surface satisfies. Now the question is that a circle in rho and theta? If it is a circle in rho and theta, then we are kind of done. Oh, sorry, we did do it, right? So you see, we have x is equal to rho cosine theta. Y is equal to rho sine theta. In general, if you go to the Cartesian coordinates, well, if you look at that expression, that is nothing but x squared plus y squared, which is rho squared, plus d squared over 4, plus d over 2, 1 plus c over 1 minus c, rho cosine theta is x. This is equal to 0. This is the expression of a circle. This you can convert into x minus x0 squared plus y squared is equal to r squared. And your circle is at x is equal to x, has a center at y is equal to 0 and x is equal to x0. So we are done. This is an equation of a circle.
Hocam şimdi hani bu circle olduğunu göstermek için Gauss law kullanabilir miydik?
No. How would you like to use it?
Çünkü hani şeyi vermiş ya lambdayı.
So?
Oradan böyle yüksek ve silindir seçim.
So?
Gauss law yazıp.
How do you choose that cylinder? What is the center of that cylinder? On the wire? You see, this equipotential surface doesn't have its center at the position of the wire. The center of this cylinder is shifted. So now in your current homework, for example, you have this the question in the other way around. In your previous homework, you were supposed to show this one basically, that the equipotential surfaces are cylinders. In your current homework, you are given two circles, cylinders. One is at a potential minus V0, the other one is at the potential plus V0, and you are required to find the electric field everywhere. Now, what you need to do is you need to, first of all, find these infinite wires, identify what should their charge be, and then this problem of two infinite cylinders is in fact the same problem as two infinite wires. They are equal in the region between the cylinders. So that is your current homework. Well, we couldn't solve a problem on dipoles, but if you ask at the beginning of the Friday lecture, I can solve it. Any last minute questions? So see you on Friday.